Hi, today we're going to continue our discussion of bonding, specifically how to name compounds. So I have here two examples of chemicals that you might be able to see or purchase or you might experience in the outside world. Really quickly attempting to name them, we're going to follow our old rules for binary ionic compounds. Binary meaning contains two elements, not two atoms. So though the first compound shows three atoms total, it's two elements, copper and oxygen. So to name these, I would name this one copper oxide. And to name the one on the right, I would name it copper oxide. I think we have a problem. Let's talk more about this periodic table. What you will see here on the periodic table is there are these groups, right? These ones in the middle, transition metals. And if we were to zoom in, there's something that we should probably make a note of that delineates a lot of the transition metals from the rest of the periodic table. The first is probably if you look, these electron configurations are atypical. If you zoom in on it, you'll see it for the fourth row. It seems like additional electrons are being filed into the third energy level. We're finishing lower energy levels. And usually that lower energy level, particularly when it comes to the compounds, will manifest in the colorful nature of the compounds of transition metals, and actually by extension some of the ones that are found underneath the staircase beyond the transition metals. But I zoomed in here for making an effect. It's shown that the potassium ion only makes a +1 charge, calcium +2, and then you get an over a bit into titanium, chromium, vanadium, manganese. Things get very interesting. What we have here is actually these are all copper containing compounds. This copper, this blue one is copper 2 sulfate, I would believe. This one's probably a copper chloride compound. The other ones get a little bit more exotic. Either there's some interesting coordination complexes going on, or maybe we're invoking a chromate ion or two. But in general, every time you see a colorful ionic compound, you can be pretty sure that there's a transition metal in the compound somewhere that's causing that color. So naming, obviously you can't have one name for two different compounds, right? Cu2O and CuO. You can't call them both copper oxide. You need some sort of delineation between them so we can have a conversation and we can all know what compounds we're referring to. That's the whole point here. So we're going to use something called the stock system for the transition metals and then for the other metals that are underneath the staircase. So on our periodic table, we're talking about this region here. Really, we're talking about any metal that has multiple charges listed. If there is more than one charge on the periodic table in the upper right-hand corner, we're going to have to use this stock system where naming the metal cation is not just using the element name anymore. We have to add something. We have to add something to say it's that specific copper or that specific nickel or that specific titanium. The way we do that is by adding a Roman numeral, sometimes in parentheses, sometimes not, usually in parentheses. So for example, if I were to say Ti2+, the name would be titanium 2. Now this unfortunately means that you have to know your Roman numerals. I'll do you a favor, I'm going to write them all below. Turns out this year you're not going to see any charges above a +7, so I'm not going to worry about going past 7, but there they are. So the really tricky thing about this naming scheme is technically if you use a Roman numeral and it's not needed, it's technically incorrect. So I'm at least going to present it that way. You would not refer to this as a scandium 3 ion, you'd refer to it as scandium because there's only one scandium and saying scandium is specific enough. So just really quickly to go down these list of 4 that are here, for these ionic compounds, if you want to pause this and do this yourself, you're more than welcome to, but is it necessary in the name to use a Roman numeral for these 4 compounds? I'm using specifically metals that are found on the screen right now. So for this one, ZnCl2, no. For NiCl2, yes, because there's a +2 and a +3 listed. For SCF3, no. And for COF3, yes. If that's unclear, again, rewind back and watch this all again. Just try again and repeat until it makes sense. That's the relatively easiest part of recognizing when this is needed. It is really important that you have a copy of the periodic table from the reference tables with you so that you have these charges listed. The link is above my head through a QR code. I've also put it on Classroom. But other than everything I just said, everything from the previous video still holds true, and we can use a lot of that and then build on it. So if I wanted a chemical formula for the compound iron 3 selenide, all I have to do is work through everything I have before. Like before, we would just write Fe and then Se. We would write our symbols from the periodic table. For Se, we can see that the electron configuration ends in a 6. It's a non-metal, so its charge is going to be 2-. For Fe, it is a transition metal that has multiple positive charges listed. Oh, good news. They gave us the 3. This literally means Fe plus 3. These mean the same exact thing. That's all you have to do. Anyway, after this, and once you have your charges, all you have to do is swap them, just like we've done before, and the formula you come up with is Fe2S3. And that's your compound. I thought it would be good to include this this table below, because this helps in the next step where we're splitting up and figuring out what the charge of the metal is. But I'm going to go through filling out this table here and then on the next slide too. So we can actually fill in from the top down for this one. The charge of the iron, the cation, is a 3+. The anion's a 2-. In the chemical formula, there are 2 and 3 of those atoms respectively, for a total of a 6+ on the positive ions and a total of a 6- on the anion side. This is not a molecule. Molecules are not ionic. So I'm just going to make that total charge. I'll have to cross it out on the next slides too. But your total charge when you add it all up is 0, and that's a good sign. That means you did this correctly. Always with ionic compounds, the sum of all the ionic charges is 0. In the case where you have a compound instead of a name, it's a little bit harder, because after you decide that yes, a Roman numeral is needed, you have to figure out which Roman numeral is needed. So unlike the last example where we're figuring out on the bottom, we're going to work our way backwards, and we're obsessively looking to fill in just this last box, because that will give us what we need. Yes, I can go through a name and I can write iron chloride. Do not forget to end in "ide," right? That's our indication that we have a negative ion here. I do see multiple charges for chlorine, but luckily 2 things are in place. It's an anion because it's a nonmetal. It has 7 valence electrons, and it's very close to having that noble gas configuration that we know is very stable, and it gets there by gaining an electron. But let's bounce through. We have some more information here that we have a chemical formula. I know that there's 1 cation and 2 anions. I know that the charge on the anion is a 1- charge. I know that the total charge has to be 0. So, knowing all this, I know that the total ion charge of the anions is a 2-, right? We just multiply to get down there. And we would divide to come back up, I would assume. This means that there has to be a 2+ total ion charge on the cations. There's only 1 cation in your chemical compound, shown here. And so that means that your total anion charge, no, you have to multiply again, it's not divide, is a 2+. And when it's a 2+, all you do is put the Roman numeral corresponding to the magnitude of the charge. The name of this compound is iron 2 chloride. So that's why I really like this table. It kind of lays everything out. You're either going from top down to figure out that all the charges balance out, or you're going from bottom up to figure out what the charge on the metal is. I put credit to, it's from, I can't remember the name of the school. It's from a college, so I borrowed it though, and I'm putting credit there. Great work for putting that together. This one you might want to try on your own. Feel free to pause if you would like to figure out the name of this compound. But I am going to get started. I'm going to do the same exact thing. So I know this is tin, and I know this is oxygen, so that's oxide. All right, we've got that "ide" there. Oxygen's real nice to you. It only has 1 charge listed. It has to be a 2-. It's the only way. There are 2 of them in your compound, and that would make a total negative charge of 4-. We know it has to be 0. That means this has to be a 4+. I see there's only 1 tin. And so the total charge of the anion has to be a +4 each. So I know this is tin 4 oxide. Now what's interesting about this is that the name is tin 4 oxide, but when you look at the chemical compound, there's no 4s. And that's what makes this, to me, slightly tricky, because you are always trying to do all this math in the background, and sometimes a Roman numeral will show up in your name that doesn't show up in your formula, and it throws your brain for a loop, because if your name is tin 4 oxide, you might expect to see a 4, but don't forget, if we were to go back from name to formula really quick, this would be tin 4 plus, this would be an oxygen 2 minus, swap, SN2O4, but we always need to have our formula in lowest, simplest ratios, and that's where you get your SNO2. And that's really hard, because to work backwards, either you have to have enough experience to know, hey, this there must have been some reduction here, there must have been some dividing here, or you have to go through this table. And if you do go through the table, you'll notice it was never even a question what the charge was. But I will say that sometimes it gets confusing, because sometimes students will just try and unswap and go, oh yeah, +2, -1, but oxygen can't be a -1, so we're not going to do it that way. That could work usually, but going this long way for now is the best way to get the right answer all the time. So to sum things up, there are some metals where you're going to have to use your reference tables, I'm sorry, and you're going to have a Roman numeral in your name. But only use a Roman numeral if you have to, because technically you're wrong if you use one when you're not supposed to. Other than that, the rules are all the same. So just to really sum things up, did you figure out what the name of these two copper compounds were? Right? We said both were copper oxide. But did you figure out which one is which? If you hadn't, it's okay. I'll fill you in now. If you were to unswap, remember that you have to do that check to make sure you got your numbers right. Copper 1 oxide is here, and copper 2 oxide is here. Again, very misleading, because the Roman numeral you might think is a number of ions, and it's totally not. It's a charge. Thanks for watching.